Section 3.9, Derivatives of Exponential and Logarithmic Functions. In this section, we're going to derive the derivative rules for exponential and logarithmic functions. First, let's quickly review logarithmic and exponential functions. We'll let b be a positive number that is not 1. F of x, which equals b to the x, is the exponential function of base b. The domain of the exponential function is the set of all real numbers, while the range is the set of all positive numbers. F of x equals log base b of x is the logarithmic function of base b. The domain is 0 to infinity, and the range is the set of all real numbers. If you recall, exponential and logarithmic functions of the same base are inverse functions. This is because y equals b to the x is equivalent to log base b of y equals x. And this is what causes the domain and range for one to be the range and domain of the other. I do suggest going back to the college algebra videos if you need a refresher on how to evaluate logarithmic functions. Both functions are continuous on their domain. So if I were evaluating limits involving exponential and logarithmic functions, the first thing I would attempt to do is direct substitution. Logarithmic functions and exponential functions have interesting limits that involve infinity. Starting with exponential functions, their graph does depend on the size of b. If b is greater than 1, we have a function that is increasing. That means the limit as x approaches infinity will be infinity because it will continue to increase without bounds. However, the limit as x approaches negative infinity, as we see from the graph, will be 0. When b is between 0 and 1, we have a graph that is decreasing. This time, when b is between 0 and 1, the limit as x approaches infinity will be 0, while the limit as x approaches negative infinity is infinity. So we have to be careful with the base of exponential functions when determining their limits, as x approaches infinity or negative infinity. Another useful piece of information from these limits is whether our base is bigger than 1 or between 0 and 1. Exponential functions have a horizontal asymptote of y equals 0. But what's interesting is only one side of our graph approaches 0, while the other side increases without bounds. Just like with exponential functions, the graph of logarithmic functions also depend on their base. If b is greater than 1, our logarithmic graph increases, but decreases when the base is between 0 and 1. As for the limits as x approaches infinity, if our base is greater than 1, because our function is increasing, f of x does approach infinity. However, keep in mind it is a very slow rise. When our base is between 0 and 1, because our logarithmic function is decreasing, our function will slowly approach negative infinity. Since the domain of our logarithmic function is 0 to infinity, evaluating the limit as x approaches negative infinity does not make sense. However, we do want to look at what happens as x approaches 0. But since we can only plug in positive values, we'll only consider x approaching 0 from the right. By analyzing both graphs, we can see that if our base is bigger than 1, f of x approaches negative infinity as we approach 0 from the right. But if our base is between 0 and 1, our function approaches infinity. This tells us whether our base is bigger than 1 or between 0 and 1, logarithmic functions have a vertical asymptote at x equals 0. One of the most important bases that we're going to work with is the number e. The number e is defined to be the number that the sequence 1 plus 1 over n to the n approaches as n increases without bounds. You'll learn more about sequences in Calculus 2, but a sequence is just a special function. Another way of stating the above statement is the limit as n approaches infinity of the function 1 plus 1 over n to the n will equal e. If we plug in really, really large numbers for 1 plus 1 over n to the n, we can obtain that e is approximately 2.71828182. There are no patterns to the decimals. That's because this is an irrational number. Because of the uses of e in modeling natural events, e is often referred to as the natural base. It is also referred to as Euler's number, named after the mathematician who did a lot of work in using e to model phenomenon. You may see e in a wide range of uses from population modeling to finances with compounding interest. F of x equals e to the x is referred to as the natural exponential function, while f of x equals ln of x, which is the same as log base e of x, is called the natural logarithm, or natural log for short. Now we're going to start discussing the derivative rules for exponential and logarithmic functions. And we're going to start specifically by using the limit definition to find the derivative of f of x equals e to the x. Before we do so, we do need a special limit, that being the limit as x approaches 0 of b to the x minus 1 over x will equal 1 when b is greater than 1. We would not be able to evaluate this limit through direct substitution because we do wind up with 0 over 0. And there is no nice interaction with exponential and polynomial functions that allow for cancellation. On the right, though, I do have the graph of f of x equals b to the x minus 1 when b is greater than 1. And you can see as x approaches 0, our function is approaching the point 0, 1. So our limit as x approaches 0 of b to the x minus 1 over x will be equal to 1. Now we can turn our attention to finding our derivative of e to the x. Through the limit definition, f prime of x will equal the limit as h approaches 0 of e to the x plus h minus e to the x all over h. If we look at the exponent of e to the x plus h, notice that we're adding within the power. Recall from our exponent properties that if I multiply two numbers of the same base, say a to the m times a to the n, that would equal a to the m plus n. In other words, when we multiply two numbers of the same base, we have their exponents. We're going to use that in reverse. Since we're adding inside of our power, we can write that as a product. So e to the x plus h equals e to the x times e to the h. Notice how e to the x is a common factor in our numerator, so we'll factor out the e to the x. Keep in mind, e to the x is now a factor that does not depend on h. Thanks to our limit properties, we can kick the e to the x out of our limit. And we have e to the x times the limit as h approaches 0 of e to the h minus 1 all over h. Well, this limit as h approaches 0 of e to the h minus 1 over h is exactly the same as the limit we were taking in our special limit property. Since e is greater than 1, then we can apply the special limit, and we have that our limit equals 1, and e to the x times 1 equals e to the x. So what we have just shown is that the derivative of e to the x is e to the x. Now that we have the derivative of e to the x through the limit process, that is the derivative of e to the x equals e to the x, we can figure out the derivative rule for the general exponential function. Before we do, keep in mind chain rule is something we always have to consider. Here, for exponential functions, we do have to keep in mind that our exponent is being put into the exponential function. So if u is some expression of x, then when we take the derivative of e to the u, where u is the expression trapped inside of our function, then through the decomposition, f of x would be e to the x, while g of x would equal u. We already know that the derivative of e to the x is e to the x, and the derivative of u is just u prime. So when we put everything together through chain rule, the derivative of e to the u is e to the u times u prime. In other words, the derivative of e to the u would be e to the u times the derivative of the exponent. Thanks to chain rule, we can figure out the derivative of b to the x. b to the x is equal to e raised to the natural log of b to the x. This is because exponential functions are base e, and natural logarithmic functions are inverse functions. One of the properties of logarithms is that powers can be brought out to the front as coefficients. So as we continue taking our derivative, b to the x equals e to the x natural log of b. Keep in mind, natural log of b is just a number. So using our chain rule that we discussed below, the derivative of e to the x natural log of b would be e raised to the x natural log of b times the derivative of x natural log of b. Keep in mind, natural log of b is just a constant. So when we take the derivative of x natural log of b, that would just be natural log of b. As for the e to the x natural log of b, reversing the work that we did to rewrite b to the x as e to the x natural log of b, e to the x natural log of b is b to the x. So our derivative rule for b to the x is b to the x natural log of b. If u is a function of x, then the derivative of b to the u would be b to the u natural log of b times u prime. In other words, the derivative of b to the u is b to the u natural log of b times the derivative of the exponent. One thing to note is the derivative rule for b to the x is a more general version of the rule we derived for e to the x. This is because the natural log of e equals 1. But since the natural exponential function is used so frequently, it does deserve to have its own standalone derivative rule. Now we're going to turn our attention to the logarithmic functions. The way we're going to come up with our rules for the logarithmic functions is by using implicit differentiation and the relationship between exponential and logarithmic functions. We'll start with the general rule for logarithmic function. That is, the derivative of log base b of x equals 1 over x natural log of b. So suppose we set y equal to log base b of x. From what we've discussed in an earlier slide, this is equivalent to b to the y equals x. Now we can take the derivative implicitly. The derivative of b to the y, which we've just discussed earlier, would be b to the y natural log of b times the derivative of y, which is dy dx. The derivative of x would be 1. From there, we can divide both sides by b to the y natural log of b. The left-hand side becomes dy dx, while our right-hand side is 1 over b to the y natural log of b. In previous problems with implicit differentiation, we did keep it in terms of y and x. But here, because I'm trying to find a derivative rule that I'm going to use over and over again, I do want to write my dy dx completely in terms of x. Well, recall from earlier, b to the y was equal to x from our rewrite that we did from y equals log base b of x to the b to the y equals x. So b to the y can be replaced with x. And we have derived that the derivative of log base b of x is 1 over x natural log of b. As for the natural log of x, the derivative of the natural log of x is equal to 1 over x. This is because the natural log of x is a logarithm of base e. So using the rule we have below, another way to write the derivative of the natural log of x, it is 1 over x natural log of e. But natural log of e is just 1. And anything times 1 is itself, leaving us with 1 over x. Even though the log base b of x rule is the more general rule, just like with natural exponential functions, natural logarithmic functions are used quite often. Therefore, they deserve their own standalone derivative rule. As far as chain rule, because logarithms use notation very similar to what we use for sine and cosine, it is a lot easier to spot the chain rule. If we assume u is a function of x, then we would apply the chain rule when we take the derivative of the natural log of u. I'm not going to do the decomposition. I'll leave that as an exercise for you. It turns out the derivative of the natural log of u is u prime over u. So it is the derivative of our input divided by our input. As for the general rule, log base b of u, that will equal u prime all over u natural log of b. In other words, the derivative of the input divided by the input times natural log of the base. One thing we need to be careful of is when to use a power rule or an exponential rule. Both power functions and exponential functions do look very similar, but there is a big difference between them. Just because we see powers, that does not automatically mean we're using an exponential rule or a power rule. We have to look very carefully at the bases and the exponents. If we take a look at our first example, y equals e to the e. E in this context is a constant. So here, the exponent and the base are constant. Well, if I take a constant, raise it to another constant, this entire value will be constant. So to take the derivative, I'm not using exponential nor power rule. Because y is constant, we'll be using the constant rule, which means our derivative is 0. However, in our next example, y equals x to the e. Here, our base contains a variable, while our exponent is constant. When our base is a variable or an expression, while our exponent is constant, that tells us we need to apply power rule. So our derivative, y prime, is equal to, now applying power rule, bring down the power of e times x raised to our power e minus 1. Now for our last example, y equals e to the x. Our base is constant, but our exponent is the variable. When our base is constant and our exponent is the variable or expression, that is when we use our exponential rules. So here, since my base is e, y prime would just be e to the x. So keep in mind, when our base is the variable or expression and our exponent is constant, that's when we use power rule, as we saw in the second bullet point. If our base is a constant, but our variable is the exponent or expression, that's when we use the exponential rule. However, if both the base and the exponent are constants, that is when we just use the constant rule. Now we're going to differentiate the following. The first will be y equals e raised to the 3x to the 10 plus 5x cubed power. Since our base is constant, that tells us we should be using the exponential rule. The exponential rule tells us our derivative is going to be equal, so e raised to the 3x to the 10 plus 5x cubed times the derivative of that power. Now for the derivative of the 3x to the 10th plus 5x cubed, 3 and 5 are constant multipliers, x to the 10, x to the cubed are power functions since the base is a variable. So applying power rule, we get that the derivative of 3x to the 10th plus 5x cubed is 30x to the 9th plus 15x squared. So y prime will equal e to the 3x to the 10 plus 5x cubed times 30x to the 9th, 15x squared. Next, we'll differentiate y equals 2.5 natural log of 10x squared plus cosine x. First, note that all the rules that we've learned before still apply. That is, constant multiplier, sum difference, product, quotient, and chain rules all still apply when working with exponential or logarithmic functions. 2.5 is a constant multiplier, so we'll have y prime equals 2.5 times the derivative of our natural log of 10x squared plus cosine x. Using our natural log rule that we discussed in the previous slide, the derivative of our natural log will be the derivative of the input divided by the input. As for the derivative of the 10x squared plus cosine x, that is 20x minus sine x. So our derivative is equal to 2.5 times 20x minus sine x all over 10x squared plus cosine x. If we want to make this look a little nicer, we can multiply the numerator by the 2.5. Next, we'll find the derivative of y equals 8 times 15 raised to the sine x plus root 3 minus x. Just like in the last problem, 8 is a constant multiplier. The 15 raised to the sine x plus root 3 minus x is an exponential function. So we're going to use the exponential rule. So we'll have 15 raised to the sine x plus root 3 minus x. Since our base is 15, part of the rule is we have to multiply by natural log of 15. Then we multiply by the derivative of our exponent, sine x plus root 3 minus x. Now we can take the derivative of our exponent, taking the derivative one term at a time. The derivative of sine x is cosine x. Then we take the derivative of the square root of 3 minus x. Before we do, we can rewrite our radical as a 1/2 power. And from there, we would take the derivative using chain rule. First, applying the power rule, we would have 1/2 times 3 minus x raised to the negative 1/2. Then through chain rule, we have to multiply by the derivative of 3 minus x, which is negative 1. From there, we can do a little bit of cleanup, and we get that y prime equals 8 times 15 raised to the sine x plus root 3 minus x, natural log of 15, times cosine x minus 1/2 times 3 minus x raised to the negative 1/2. Next, we're going to take the derivative of y equals x cubed times log base 4 of 5x squared. Recall what I said earlier, rules like product rule and quotient rule still apply. We have x cubed times the log base 4 of 5x squared, and this multiplication would be the last operation we perform when simplifying. Therefore, we need to apply product rule. The derivative of x cubed is 3x squared, and we keep the second log the same, so times log base 4 of 5x squared, plus, now we keep the x cubed the same, and we multiply that by our derivative of log base 4 of 5x squared. Because our base is 4, our numerator is still going to be the derivative of our input, and the derivative of 5x squared is 10x. As for the denominator, we still have the 5x squared, but because the base is 4, we have to remember to multiply by the natural log of 4 in the denominator. Note how I didn't write out all the primes. I took derivatives as I went. As you get more comfortable with these rules, ideally this is what you want to be able to do. You identify what rule to use, and you start taking derivatives as you go along, writing out that rule. If you are not comfortable yet with the rules, you can always still break it down like we have in past sections. We can do some simplifying in the last term. The x squared will reduce with the x cubed, leaving an x. Also 5 and 10 also reduce, leaving us a 2 in the numerator. So our last term simplifies to 2x squared over natural log of 4. And our y prime is equal to 3x squared, log base 4 of 5x squared, plus 2x squared all over the natural log of 4. Last, we're going to take the derivative of y equals log base 2 of x squared all over e to the x minus 1. Here we can see the last operation we would perform if we were simplifying is division. That tells us we would be applying the quotient rule. First, for the derivative of the numerator, applying our log rule, the derivative of the input is 2x all over the input x squared times natural log of 2. We're going to multiply that by our denominator, e to the x minus 1, minus, now we'll keep our numerator the same, multiply that by the derivative of our denominator, which would be e to the x minus 0, which is just e to the x. Keep in mind that the derivative of x is 1, so chain rule wasn't really necessary here since we were just taking the derivative of plain old e to the x. All of that will be over our denominator squared. Just like before, there is a little bit of cleanup we can do. The x's cancel in the first term, and in the second term, we'll just rewrite the order of our factors, putting the e to the x in front of the logarithm. And we get that y prime equals 2 over x natural log of 2 times e to the x minus 1 minus e to the x log base 2 of x squared all over e to the x minus 1 squared. You could go a step farther trying to clear the denominators. I'll leave that as an exercise for you all to practice.